Okay, so welcome everyone to our afternoon session. I hope to lunch everyone find a restaurant or somewhere to eat. And yeah, and we have another talk about some LambdaPi deductive thing.
Yeah. Okay. So
reset the camera because it's tracking me, and you don't want the camera to track
camera reset.
Yes.
Yeah. I learned this last week.
I think you have to press.
Yeah, you need to press.
twice.
Yeah, just keep it until, yeah.
There we go. Excellent. Okay. So I'm going to talk about our work, me and Guillaume did last year on translating from Eunoia, which is a logical framework for SMT solvers, to LambdaPi, which is the successor to deductive. And yeah, this work was done by me and Guillaume last year, whilst I was funded by Eunoia. Now I'm funded by Telecom, but we did this ENS within deductive. And I believe that we have the full hour and a half, so I suppose we can go slowly. So if anybody wants to ask questions throughout and make it more of an interactive experience, then we can do that. The clicker doesn't work. How do I make this work? Am I just
is
stupid?
it on? Well, the first question is it
Did
on?
you put the USB part in your on your computer?
It's this computer. It's the same computer.
Probably worked earlier.
No, it worked.
Ah, okay, yeah, excellent. That will help. Excellent, thank you. So firstly, what is Eunoia? Eunoia is an emerging logical framework for formalizing the proof systems of SMT solvers. The development is led by Andy Reynolds at the University of Iowa. It's the spiritual successor of the ELECT proof format that maybe we saw in Alessio's talk. Sorry, I wasn't at Alessio. And I was working on these slides. And as well as doing the proofs, Eunoia also covers the signatures of the theories themselves that the proofs are about. And it has this checker called ethos, which is used to check the signatures and the proof scripts. So Eunoia can be seen as extending the standardized SMT lib by adding dependent types, parametric polymorphism, programs which are just constants with rewrite rules. You can also declare inference rules, and you also have commands for building proof scripts. What is LambdaPi? LambdaPi is a logical framework based on the LambdaPi calculus modulo rewriting. The development is led by Frederic at Eunoia, and we have a small code base, and because we're working in the LambdaPi calculus, we have some reasonable trust in our foundations. It's a very, very fast type checker, possibly even faster than the original deductive type checker. And we can also do interactive theorem proving with LambdaPi using the language server protocol. So we can do this in VS Code or Vim or any editor you want. And the main focus of LambdaPi is on interoperability, as we all know here. The cooperating proof calculus is CPC5's proof system, which is formalized as a Eunoia signature that we'll call Sigma CPC. And it's not a small proof system. It's not like natural deduction where maybe you have 10 rules or something. This has over 600 inference rules in the current build. And also some of these rules take term arguments, and some of them have side conditions and stuff like that. So it's quite a funky system. And the proofs that are now produced by CPC5 are Eunoia proof scripts that will exclusively use these rules that are formalized in the signature. So for example, here is one of the rules from CPC that does elimination on NRE conjunctions called and elim. And then here it is formalized in Eunoia. So you have this, can I do a little pointer thing? Yeah. So we can have this declare rule command, and we say and elim, and then this is a bit like a context. And then you say, okay, we take a proof of fs, we take an argument I, and then we return the nth element of this list f, the ith element, sorry, using this thing here. So for example, the following problem is unsatisfiable, and CPC5 will give us a proof demonstrating this. So yeah, if we try to prove P and not P, then we obviously get unsat, and we get a proof that looks like this, where you have some assume and P not P, and then a bunch of proof steps, and then we end with false using the and elim rule, and then the contra rule. And you can see we give some premises and some arguments for each of these things. And yeah, the format of the rules is always like this, as we'll see. So our goal was to design a translation procedure T, such that if sigma is some Eunoia signature that implements some logic L, then T of sigma should be a LambdaPi signature that also implements that logic L. Thus, if pi is a valid Eunoia proof script that depends on sigma, then T of pi should be well typed in LambdaPi with respect to the translated signature T sigma. So let's have a look at Eunoia. So for the syntax of Eunoia, we just have a set of symbols, and then the terms are defined as just either a symbol S or an application of a symbol S to a list of Eunoia expressions E1 to EN. And in general, our expressions are either terms like true and false, types like bool, or arrow types like bool, arrow, bool, or kinds like type and arrow type type. And yeah, in SMT in general, we use prefix notation, so it's a bit weird, but you get used to it. Ooh, did I go? What happened? Okay, it's fine. So Eunoia has type declarations. So this is kind of something that they have in earlier versions of SMT, but here it's a bit more unrestricted. So for example, you declare some symbol and then you give your arguments here. So for example, the array type is a binary type constructor. So it says, okay, we take a type, and then we get a type back. And then for constant declarations, we have a symbol S, and then the type E, and then an optional constant attribute, which modifies the application strategy and how things are elaborated. So you have things like right to sock nil, left to sock nil, and some of these can take an optional term or an optional symbol as well. So for example, you have the declaration of the right of the and constant, which is declared to be right associative with the so-called nil terminator true. So this is, yeah, the declaration. We say, oh, it has this type, and it has this attribute here, and it has the true term. And then this means that the n-ary applications of and like this will be unfolded into a sort of listwise form like this, with true terminating at the end. We can also declare what are called parameterized constants, and this is basically how they do polymorphism, and also how they do dependent types. So here, these rows are what they call typed parameters, which is just some symbol, some type, and then what's called a variable attribute. So this is similar to the constant attributes, but here we just have implicit and list. I don't think we'll go over list in this talk at the moment, but implicit is there. Obviously, here we have the declaration of equality, where it takes this type argument of A, and then its type can be A, arrow, bool. And also equals is declared to have this chainable attribute, which then means that in an application like this, of course, because it has the implicit type argument and it's polymorphic, we don't have to give the type argument and it will just be inferred. But then it also means, because we have this chainable with the and, it means that X, if we're trying to say equals X, Y, Z, this will unfold to, yeah, this. Eunoia can also define symbols that are basically like macros, and you can optionally give some type, and similar where you give some parameters as well. And this is just an example of some definition from CPC. We also have these programs, which are, yeah, you give the symbol, some parameters, the signature of the, so basically the type of the symbol. These are the types of the arguments that you're giving to the program, and this is the return type. And then you just give an ordered list of rewrite rules, basically. So this is one of the rules that converts things to OR clauses. The meaning of the rule isn't important, it's just the overall syntax. And we also have these rule declarations where we can declare a rule, we give some parameters, we give the premises, we can also give arguments, and then we also give a conclusion. So here, this is an interesting example, because from what I understand, in the older proof formats like LEP, resolution is a bit complicated, and you have to do lots of reconstruction if you want to port proofs that do some resolution in it. But here, it's just handled by this one rule, and all of the complicated stuff is dealt with in this program that's called resolve. Yeah. And then for the proof scripts, the two main commands that we'll look at are this one, assume, and then this one, step, where you say, okay, we're making a step, there's the name for the step, that's the formula that we're concluding, which is optional. You say what rule we're using, and then you give the premises and the arguments, as we saw earlier. Okay, so that's Eunoia. For LambdaPi, we have terms which are given by the LambdaPi calculus. So just variables, applications, lambda abstractions, and pi abstractions. Our symbols are declared like this, where we give symbol, some LambdaPi parameters, and then some type. So the LambdaPi parameters can either be explicit or implicit parameters. Symbols can also be defined, where the type is optional. Rewrite rules are declared like this, where you basically just give a list of all of these different rewrite rules, which are just pairs of terms. And we encode, when we're encoding type systems, we use type universes, Tarski style, which are closed under this arrow operator. So we have a type set and then a constructor L, which maps any set to the type of its elements. And then we have a function space operator, which takes two sets and gives a set of all of those functions between those two sets. Proofs are encoded similarly, where we have a type for propositions, and then we have a proof operator to lift propositions to types. So for example, we might have an equality operator. What did I do? How did I do this? Okay, fine. So yeah, we have an equality operator that takes an implicit type argument and then takes thing of type alpha returns a rule. And then we have a rule that involves that symbol where we have two implicit arguments and get a proof that x equals x. Now for the translation itself. So our goal was to take a Eunoia signature and generate the corresponding LambdaPi signature T sigma. So to do this, we process each command in Sigma and we update some environment data as we go. So we take some signature with the head C, we translate C, so that should actually be C prime. And then we continue translating with some updated theta prime. And our translation tool, EO to LP, was written in OCaml, and we use Menhir and stuff for parsing. But the following is just a high-level sort of abstract overview of the translation. So first, before translation, we need to do elaboration. And we parameterize elaboration by this function gamma, where gamma tracks the attributes of the symbols. So Eunoia actually has a built-in symbol underscore, which is used for higher order application. And the default elaboration strategy when a symbol has no attribute is to basically just fold leftwise using this underscore. So this is just a shorthand notation for writing this kind of explicit binary application. So we basically want to convert everything from these n-ary applications to binary applications because it's easier for us to handle our translation like that and actually get things to type check and LambdaPi. So in general, whilst that's the default strategy, the strategy will depend on the attributes of symbols. So as we saw before, the and symbol has the right assoc nil attribute. That should be true. That's a typo. So then therefore, this application will elaborate like this. When we're translating the kinds of Eunoia, we translate these into LambdaPi types. So when we have the constant or the symbol type from Eunoia, we translate this to set. And then when we have arrows that are building kinds, we basically just descend on our translation until we reach something that isn't from these two cases, in which we know it's probably a type, or it's probably a Eunoia type, and it needs to be converted to a set. So therefore we apply L and then descend into the translation and use this separate term translation, which I'll show in the next slide. So for example, to see why we need this here, this is because they have these kinds that look like this, right? Where you have a family of types indexed by integers, and we want it to convert to this, basically. That's how you do that. So therefore, we can easily translate Eunoia's type declarations. So if we have declared type t to e1 to en, all we do is do symbol of t, where we basically escape so that we can translate any name from Eunoia to some LambdaPi name here. So that's what those curly braces are. And then, yeah, we just translate the type, which in this case, yeah, we just descend onto all of them and replace the arrow with LambdaPi's arrow type constructor and inset. So for example, we have declare type array, which takes type, and then this ends up just being, oh, yeah, okay, that's a mistake as well. That should have an extra arrow set on it because it's a binary type constructor. And then for translating the terms, it's fairly simple. We just match on symbols, and if the symbol was this arrow, then we translate to the squiggly set arrow, which is within our encoding. And otherwise, we just translate the name of the symbol. And then for binary applications, we just descend. So we can consider translating the following type. And yeah, it's as expected, where we descended to the bit back in 5 here, and, which then makes it easy to translate constant declarations like such. But here we see that the type that we get is going to be some set in here. So whereas before we were translating into LambdaPi terms of type, here we're translating into LambdaPi terms of type set when we're operating on here. And also, whilst we're doing this and we're translating this constant declaration, which may have this attribute alpha, we also need to update our attribute map gamma with this mapping from S to alpha. Of course, the translation of implicit parameters is easy because we support these directly within LambdaPi. So yeah, whenever we see one with the implicit tag, we just use the square brackets instead and descend with our translation, of course. And then this makes it easy to translate parameterized constants because we just translate the parameters and do the same as we were doing on the within the type here for the actual type of the constant. So for example, on the equality one here, this ends up as expected with the implicit parameter for the A and then the correct type here. Definitions are translated like that. Programs are translated. I got tired of doing the abstract syntax, so you'll just have to trust me that we can translate them with this example. So this is an example of translating some program. It's quite simple. We just translate the left-hand side and the right-hand side of the rewrite rules. There does need to be some inference of explicit arguments here, which can be done like before translation, but it's a bit annoying that we have to do that. But it's necessary in some cases to make sure that it actually means the right thing. And also, it's assumed in Eunoia that the lists of rewrite rules that we give are executed sequentially. So we need to use in LambdaPi the sequential modifier for our declaration of this symbol so that it does it in the correct order. Because otherwise, if we didn't have this sequential, we would always just be matching on this and this program would do nothing. Whereas with this sequential thing, it will always try first to match on this pattern. The rule declarations are also translated. Once again, you just have to trust me. But these are a bit different because we basically have to generate these auxiliary programs in order to handle the arguments for rule declarations. So I can show that on a better example of why we need to do that in a moment. And yeah, we can translate the proof scripts. So for example, here is an example of one of the proof scripts that we translated that has about 9 steps. And yeah, it all works and it all checks. So as for the results themselves, So whilst I set up this ambitious thing that we're going to be able to translate any logic in Eunoia and all 600 rules of CPC, under the advice of Haniel himself, we decided to focus on the fragment of CPC that supports the QF-UF fragment of SMT-lib. So that's quantifier-free uninterpreted functions. So this is probably the smallest part of SMT-lib. So in order to carve out this specific portion, because it's not fragmented this way, we looked at some SMT-led benchmarks for QF-UF. So in particular, we looked at the Rodon benchmark, which has some 30 ONSAT problems. And then we run CPC5 on all of those problems with proof format CPC, which is the default argument. And then we dump all of the proofs. And then we analyze all of those proofs and we check which rules were used. And then we calculated all of the dependencies within the signature of that. And then we make some modifications to that. And then we call this fork CPC mini. We translated all of CPC mini to LambdaPi using our tool EuroProofNet. And we translated all of our Rodon proofs and everything checked and everything was fine. I wish that I could have some examples and stuff to show you there, but yeah. And yeah, there's lots of potential for future work in our stuff. So for example, we want to support the entirety of CPC so that we can do arithmetic, strings, and bit vectors. And this doesn't seem too hard. Eunoia has changed a lot over the past few months since I wrote all of this code, and things have gotten significantly simpler and more in line with what's going on in LambdaPi. And also the way that I've been thinking about this stuff has changed too. We want to scale up to bigger proofs. The proofs from the Rodon library only had at a maximum of about 70 steps or something, but it's still good that we could do this. But as I know that there are some proofs that have over 100,000 steps in them and stuff, so we need to be able to check these things as well. We need to tidy up the translation. So for example, at the moment, lots of the phases of the translation happen in our OCaml program. However, I think that it may be possible to perform the elaboration and the interpretation of basically the syntax trees within LambdaPi itself, which could be an interesting approach. And yeah, it would be nice to do all of this in Brazil in November 2025, as we'll be visiting Haniel again there for 3 weeks. So it will be a good time to begin working on all of this stuff. Yeah, that's it. Thank you. Does anyone have any questions?
Yes, questions. Yeah. I mean, you've been a bit too fast.
Oh, sorry.
This program stuff. I
Yeah.
understand what it's. I mean, I don't understand how general programs are, and if you can always translate them, and does it mean that basically you're done? Because I mean, I had the impression that programs were a bit like side conditions that you had in LFSC in the old times.
Yeah.
And you could actually put anything you wanted there, and that was dangerous because if you want to have a translator of proofs.
It's very dangerous. And in the version of Eunoia that I was working on at the time when I wrote the translation, they were doing some crazy stuff inside these programs. And lots of the times they weren't even giving the types for the programs. So I was having to write my own type inference engine in OCaml to do all of this stuff and calculate the types beforehand. So it was a mess. But now they've changed things so that they have this signature thing, which is helpful for one. But also what they were doing in the past is they could basically match on arbitrary applications of symbols. So this caused me lots of problems. And that was one of the motivations to work on this smaller base of QF-UF, because at the start I was like, how do we deal with all of this complexity? So that's what I mean when I say, oh, we had to make some minor modifications to our fork of CPC because there were some in fact, there were some inference rules that used programs for side conditions that involved this kind of thing. But fortunately, I was able to isolate those specific cases and deal with them explicitly. And there was only one case in which I needed to do that. And I basically needed to like go into a term, insert n many explicit applications, and then modify my version of the program so that rather than matching on normal applications, it would match on these explicit applications. But I think that, so that's why I was saying about, oh, it would be nice to perform the elaboration within LambdaPi, because I think if I was performing the elaboration within LambdaPi, I could translate these programs that do these arbitrary matches and stuff, because I would be working on a more explicit representation of the syntax trees rather than this shallow way where the applications of Eunoia are explicitly the applications of LambdaPi. And there are many other issues with programs that I had to deal with. And now lots of those issues have basically evaporated because CPC has been changed a lot and Eunoia has been changed a lot. Another thing as well was that they had these arbitrary match terms as well. So the nice thing about programs, at least, is that they are named, right? They have some name attached to them, but they had these match terms, which were basically just inline programs, and then they could be nested. And yeah, so I had a whole procedure for eliminating these match terms and making these auxiliary constants and dealing with the variable environments and stuff, but then now they're gone. They don't exist in Eunoia anymore. So this is the nature of working on something that's moving quite fast.
Other LambdaPi questions then?
Yes, go for it.
I mean, the definition of programs on other rules with programs are very different from what you would naturally do in LambdaPi if you define what you mean by doing propositional logic, right? Or QFU logic. And then if you want to share proofs or if you want to to communicate proofs from one system to another, you must then reconcile those notions. So you would have to kind of prove that your program are valid in, I don't know if you understand what I mean here, that you would have to prove that the programs are valid in propositional logic, that you would define in some other way. I mean, I'm talking about the resolution rule.
So my initial thoughts on that are like, at the moment, what's happening when we declare these programs? Let's look at an example of a translation of a program. Yeah, right. Okay, so we define this sequential constant and then we define these rewrite rules. And then this means that type checking is happening modulo these rewrite rules, which means that when I process these proofs, it happens pretty easily because I don't need to explicitly say and use this program and call this program and call this program, etc. It all just happens. If I understand correctly, maybe like what's related to your question is you could perhaps make those program calls explicit. So like when you replay the proof, you could see what programs were called during that thing. And then that might make it easier for translating to some other system, but I'm not sure. I just saw the obvious parity between the programs in Eunoia and the rewrite rules that we have in LambdaPi and went, okay, it works, great. But yeah, you may want to like have some explicit recording of saying, okay, we do this and we do this and we do this. But yeah, I suppose some of the rules, there could be some concern that some of the programs themselves aren't even definable in first order logic or something, but I don't know. A bit like that's in relation to what you said about the programs being valid. And I don't know what you mean by that necessarily. So
do you mean that would it be possible to prove the correctness of the programs? For instance, the resolution, the program for resolution to prove that.
Well, I mean, the programs are a kind of definition of the logic that you are working with.
Yeah.
And it's kind of completely different from what we've seen in previous talks. But it's the same logic, so you would have to reconcile those two.
Yeah, well, okay, one part of that question is, one part of my answer is, it's not my problem. that's Haniel's problem or the Eunoia people's problem. And if they have some argument for why their programs are all fine, then sure.
It's rather the LambdaPi problem, because you are using LambdaPi in a way that it's kind of very different from what other people would do. Right?
So then, in answer to that, that's Frédéric's problem, because he needs to, because he gives some guarantees about, oh, when you define a theory and you define programs, blah, 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 we have a model based on blah, blah. And then if you change, so I believe it's the case that when you have this sequential modifier, this actually breaks some property that we care about for, I don't know, theoretical things. So perhaps there's a way that, and maybe it's nicer than if you can encode these things just as non-sequential symbols, and there's some way of transforming the rewrite rules so that they happen in the right order, or yeah, I don't know. Maybe there's something the Eunoia people can say about that as well, but I guess, yeah, I was kind of left to my own devices because the Eunoia documentation is very much operational. They say this command does this thing, this command does this thing. And then when it comes to giving a sketch of the type system, their first rule, as Alessio laughed at when we first saw it, their first rule was type in type. So it's somewhat lacking on the theoretical side, but hopefully I believe Hans has been doing Agda formalization as well. So maybe that will enlighten all of us as to what the role of these programs are. But they seem somewhat necessary in order to do this nasty stuff of resolution in a more modular way, rather than this sort of bespoke, oh, the documentation is in the source or it's in the alert PDF or something like that. So, yeah. Yes.
I have a quick question. Probably it's related to the previous slide with the parameter constants like parameters.
Mm-hmm.
Yeah, so what do you mean by uninterpreted functions? You mean by uninterpreted function terms, probably, expression.
Yeah, I don't know. I don't really like that phrase anyway. I see that phrase used in the like SMT documentation in the SMT lib world, and they say uninterpreted functions, and I don't know what they mean by this.
So I guess it's
it seems that they just mean
it's a
free
function
variables.
term. It's a name of a function which is not interpreted.
But it seems to be in reference to like the model theory, that because we're talking about interpretations, and it would be nice if Eunoia was connected to the model theoretic world of SMT, but not yet.
I know how I did the uninterpreted things, because in programming language, typically you cannot have free variables. You have to interpret them. And I used in this dependent type theory situated, which I didn't call it dependent because it's a recursive system. So I used it semantica, like what you say, models, but mathematical structures without any interpretations between symbols. And in the model, in the mathematical structure, I had probably what you had there. Constants like parameters, and variables, I used to call them. So you introduce in the model system, in the mathematical structure of all types, parameters, semantical level. They can be anchored to any specific object, even that object can be partially specified. And that gives very nice, uninterpretable.
Yeah, interesting. So this is more to do with the semantics of, of SMT stuff, which is interesting.
Now I do it formal language, and I don't know how yet to do it without these semantical parameters.
Yeah. So as for the semantics of SMT 2.6 are the last ones I saw. I don't know how they've changed things for 2.7 now that they have lambdas and stuff. But then to have semantics for this, it's a bit different because we have this type constant and stuff. So you need to go a bit bigger in terms of the set theory that you're using or the size of your models and stuff. But perhaps there are some clever tricks that you can get around it by using.
The clever trick is there to skip off the foundation axiom and to replace it, not just freely to skip it, but to replace it with anti-foundation axiom.
We should talk. That's this is my latest shtick is anti-foundation.
You get proper classes, but still good ones that you can handle in finite graphs, memories. And here, this trick with the parameterized constants is a good trick because this touches decidability. Constants without this making them like parameterized.
Yeah.
They can be interpreted in who knows whatever way, even if they are finite numbers.
So I suppose I should
And
stress.
this is a very good way to avoid that problem.
I suppose I should stress that all of this is just syntactic, right? I'm just
Yes.
describing the abstract syntax of Eunoia and how we translate into LambdaPi.
Yes.
But
That's the
what you
thing.
say is interesting, and I will look into it. And we should definitely talk about normal founded sets and how you get proper classes using normal founded
Yes,
sets.
I'll tell you how on the blackboard.
Yes, okay.
Even if
Excellent.
we have time now, we can do it right now.
Cool.
So I have one question before, and afterwards we have discussion time. So you can discuss that if you want. So you just
It's a
at
very
the,
nice thing here.
yeah.
Thank you.
At the beginning you sold LambdaPi as a successor of Deducti.
Yeah, sure.
Is it?
I'll let Frederic answer, I suppose.
Nobody is working on Deducti anymore.
Yeah, I don't know. Yeah. I've seen those words printed somewhere saying it's the successor. I've seen Deducti 3.0 listed or interactive Deducti and things like that. So yeah, the ecosystem confused me for the first few months as I was working, and I was like, what's the relation between Deducti and LambdaPi? How am I meant to know which one I should be using? And but yeah, we just use LambdaPi because I guess it's just as fast as using Deducti. The syntax is nicer. I can do interactive proving, and yeah, it's just.
And is it backwards compatible? So in the sense of
Yes.
some of this translation, I think are older than LambdaPi. I'm not one.
Yeah, I suppose this one's even called Isabel DK. So the name I think so. But yeah, LambdaPi can check Deducti files, and it can also export LambdaPi files to Deducti files. So there's a parity, but maybe there are some problems. No, it all works perfectly.
Yeah,
Okay, great.
No. Yeah, perhaps there are small things that are not fully compatible, but I mean, for 99%, it should be fine. Okay. So yeah, I mean, so LambdaPi is not. I don't know if we can say that it's the successor of Deducti.
That's why I didn't write it.
Yeah,
It fell out of my mouth,
Because
but I didn't write it for that reason.
It doesn't mean that we are not using Deducti anymore. I mean, of course, I mean, if we can get LambdaPi as fast as Deducti, then perhaps we may not need Deducti anymore, but this is not yet completely the case. Although we improved the efficiency of LambdaPi recently. So yeah, and so the use it's a little bit different. So so Deducti is much simpler, but you need to provide the proofs completely. I mean, with no implicit arguments, nothing, no holes. And while in LambdaPi, so it may be used as intermediate step between the two, because you have more features to elaborate full proofs.
And I guess comes the question we partially had during lunch: why name the system differently?
Yeah,
Why
yeah.
is it just Deducti interactive?
Well, it's, I mean, yeah, it has been done like this, and we just kept the names.
Any more questions? Let's thank Ciarán.